Introduction. Welcome, everyone. Let's begin our lesson on the extended chain rule. To start, let's look back at what we have already covered. In the previous section, we learned the basic chain rule. As you recall, the basic chain rule provides us with the method to differentiate a composite function consisting of just two functions. For instance, a function f of g of x. However, as we progress into more advanced mathematics and physics, we will frequently encounter what we call deeply nested functions. These are essentially functions within further functions. To handle these complex structures, we use the extended chain rule, which is a generalization of the basic chain rule you've already mastered. Essentially, this rule allows us to find the derivative of a function composed of 3 or more layers. We do this by differentiating each layer one by one, moving systematically from the outermost layer to the innermost layer, and then multiplying all those resulting derivatives together. In the following slides, we will dive into the formal definition and a step-by-step process to ensure you can apply this rule accurately. The formal definition. Now that we understand the concept of deeply nested functions from the previous slide, let us look at the formal definition of the extended chain rule. Suppose we have a function f that is a composition of 3 different functions, w, u, and v. In mathematical notation, we can write this as f equals w composed with u, composed with v. To make this process easier to manage and to avoid confusion, we can decompose the function into a sequence of intermediate variables. Think of this as breaking the function down into layers. First, we let t equal v of x, which represents our innermost function. Next, we let s equal u of t, which is our middle function. Finally, we let y equal w of s, which is the outermost function. According to the extended chain rule, the derivative of y with respect to x is simply the product of the derivatives of each of these layers. This is expressed as the derivative of y with respect to x equals the derivative of y with respect to s, multiplied by the derivative of s with respect to t, multiplied by the derivative of t with respect to x. If we write this in terms of our original functions using prime notation, the derivative of f with respect to x equals w prime of u of v of x, multiplied by u prime of v of x, multiplied by v prime of x. While this formula may look intimidating at first, it is essentially just a chain of multiplications. In the next slide, I will walk you through a clear, step-by-step process to ensure you can apply this rule without making any errors. Step-by-step process for differentiation. Now that we have established the formal definition and the general formula in the previous slide, you might be wondering how to practically apply this to a problem without getting overwhelmed. When you are faced with a complex nested function, I recommend following these 5 systematic steps to ensure accuracy and avoid errors. First, identify the layers. Take a close look at the function and determine the order of operations. You should think of this like peeling an onion. Identify which part is the innermost function, which is the middle layer, and finally, which is the outermost function. Second, assign variables. To make the mathematical expressions more manageable, assign a temporary variable, such as u, v, or t, to each of those inner functions. This simplifies the notation and helps you keep track of each layer independently. Third, differentiate each layer. Now, find the derivative of each individual function with respect to its immediate input. For instance, if you have defined y as a function of s, you will find the derivative of y with respect to s. Fourth, multiply the derivatives. This is where we apply the formula we discussed in the formal definition. Simply multiply all those individual derivatives together in a continuous chain. Finally, perform back substitution. Since your final answer must be expressed in terms of x, replace those temporary variables like u, v, or t with their original expressions. This will provide you with the final, complete derivative. In the next slide, I will provide a real-world analogy to help you visualize why this multiplicative process is necessary. And then we will put these steps into practice with a detailed worked example. Real-world analogy, the gear system. Now that we have covered the formal definition and the step-by-step process, let us use a real-world analogy to make this concept more intuitive. Imagine a mechanical system consisting of 3 connected gears: Gear A, Gear B, and Gear C. In this setup, Gear A turns Gear B, and subsequently Gear B turns Gear C. If you want to determine how fast Gear C is rotating relative to Gear A, you cannot simply look at the first and last gears in isolation. Instead, you must multiply the ratio of Gear A to Gear B by the ratio of Gear B to Gear C. In other words, the total rate is equal to the rate of C relative to B, multiplied by the rate of B relative to A. Similarly, in the extended chain rule, the rate of change of the final output depends entirely on the product of the rates of change of every intermediate layer we discussed in the previous slides. With this conceptual understanding in place, let us move forward to a worked example to see how this logic is applied to a mathematical function. Worked example. Now that we have discussed the theoretical framework and the gear system analogy, let us apply these concepts to a concrete problem to see how the extended chain rule works in practice. Our objective is to find the derivative of the function y equals sine of cosine of x squared. Following the step-by-step process we outlined in the previous slide, we begin with step 1, identifying the layers. If we look at the function from the inside out, we can see that the innermost function is x squared, the middle function is the cosine function, and the outermost function is the sine function. In step 2, we assign temporary variables to these layers to make the differentiation process more manageable. Let us let t equal x squared, s equal cosine of t, and y equal sine of s. Now we move to step 3, where we differentiate each layer individually with respect to its immediate input. First, the derivative of y with respect to s is cosine of s second. The derivative of s with respect to t is negative sine of t, and finally, the derivative of t with respect to x is 2x. For step 4, we apply the extended chain rule formula by multiplying these individual derivatives together. The derivative of y with respect to x is equal to the derivative of y with respect to s, multiplied by the derivative of s with respect to t, multiplied by the derivative of t with respect to x. Substituting our previous results, we get cosine of s times negative sine of t times 2x. The final step is back substitution. Since our original problem was in terms of x, our final answer must also be in terms of x. We replace s with cosine of x squared and t with x squared. This gives us cosine of x squared multiplied by negative sine of x squared multiplied by 2x. To present this in a standard mathematical form, we rearrange the terms to get negative 2x, sine of x squared, cosine of x squared. Please take note of how we meticulously accounted for every single layer. As we will discuss in the next slide, forgetting to differentiate the innermost layer is one of the most common errors students make. Common mistakes to avoid. Now that we have walked through a concrete example, let's discuss some common pitfalls to ensure you do not lose marks when solving these problems. First, be very careful not to skip the innermost layer. A frequent error is to differentiate the outer layers, but forget to multiply by the derivative of the very last inner function. If you look back at the worked example we just completed, forgetting to multiply by 2x would have led to an incorrect final result. Second, pay close attention to the order of composition. Some students mistakenly attempt to differentiate from the inside out. To avoid this, always remember to work from the outside in, or strictly follow the product of derivatives as we defined in the formal definition. Finally, let's address confusion regarding power notation, as this is a common area of struggle. Be particularly careful with notations such as sine cubed of x. It is important to recognize that this is actually a composition where the sine of x is raised to the power of 3. In this specific case, the outer layer is the power of 3. and the inner layer is the sine of x to take this a step further. If you were to encounter sine cubed of 2x, you would actually have 3 distinct layers to differentiate. First the power of 3, then the sine function, and finally the 2x. Identifying these layers correctly is the key to applying the extended chain rule successfully. Keep these common mistakes in mind as we move toward our final key takeaways. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of this concept. First, remember that the extended chain rule is the tool we use whenever we encounter functions composed of 3 or more layers. Those deeply nested functions we discussed at the beginning of the session. Secondly, keep in mind that the formula is essentially a product of derivatives. To put it simply, the derivative of y with respect to x is equal to the derivative of y with respect to s, multiplied by the derivative of s with respect to t, multiplied by the derivative of t with respect to x. This is the mathematical equivalent of the gear system analogy we looked at earlier, where the total rate of change is the product of each individual stage. Thirdly, let's recap the workflow we used in our worked example. The process is a systematic sequence. You start by identifying the layers from the outside in, then you differentiate each layer individually, multiply those derivatives together, and finally, perform back substitution to ensure your final answer is expressed in terms of the original variable. Ultimately, the most important thing to realize is that the extended chain rule isn't a completely new concept. It is essentially just a repeated application of the basic chain rule. Once you are comfortable peeling back one layer at a time, you can handle a function regardless of how many layers it has.